Okay. Hello, everybody. Thank you so much for having me today. Today, I'm going to talk about neural embedding network, ultrasound silent speech interface, which this is a part of project, which is silent speech interface with collaboration Hungarian universities. And I'm a PhD student from Szeged University in Hungary. So what is exactly silent speech interface is? Silent speech interface is translating articulatory signals to acoustic signals. For example, we can consider these articulatory signals as lip movement or tonic movement or brain signals or face movement as well. But how we can record this articulatory signal? We can use it, for example, as ultrasound video imaging, put it under the jaw, or by a camera of your mobile, or we can use fMRI or EMG or some other devices for recording every signal regarding to the speech. And after that, we have to translate it to a speech. So how we can do it, we actually, for example, we put ultrasound probe under the jaw, and at the same time, we record speech by microphone, and we record ultrasound at the same time. So we extract features like millispectrum from the speech, and then we have ultrasound at the same time. Then we put this millispectrum as output of the model. Then we train the model to predict this millispectrum and then synthesize a speech from the millispectrum, which is synchrony with ultrasound. But there is a problem here. For example, when we are synthesizing a speech from multi-speakers, we have a lot of, for example, we have a lot of speakers, and each speaker goes to a different session, and each session there are different parameters which have to be tuned. For example, we have to tune each session for each speaker, this ultrasound probe will be reallocated, or there will be some background noise, or there will be some anatomy different for each speakers. For example, I don't know, the place of the tonic or jaw is different. So there are different parameters which have to be tuned. And for training better for convolutional neural network or deep neural network, we need to have a lot of data set. So this multi-speaker would consider as independent synthesizing because we have a lot of speakers and each speaker different session. But for one speaker, it would be much more easier because the parameters is less and we have a lot of data just for one speaker. But how we can solve the problem for independent synthesizing when we have multi-speakers and less data and a lot of parameters which have to be tuned? So the solution here came by I-vector and X-vector. I-vector can use, for example, hyperparameters and then use total variability and then extract I-vector, which this I-vector consider as a description for each person characteristics. But calculating I-vector needs to some training hyperparameters. So another similar method came with names of X-vector, which is they named it X-vector because it do the same like describing each person characteristics. So and it is much more easier. It's just according to deep neural network, then there is some layers which extract features, and then a statistical layer which could be global average pooling or a standard deviation or matching network, and after that some layers which can extract X-vector features, which is a constant vector, but the input could be a different variant of utterances. So how we can use and implement this X-vector, there is 3 steps. As I told, the first step is some layers which can extract features, and then statistical, and then output layer for training these X-vectors. Here also there is another. So in our work for synthesizing a speech and generalizing for unseen speakers, we used a TIL80 dataset, which is from University of Edinburgh. There are 81 speakers there, and it's publicly accessible. And there is another TIL-1, which is for language dependent for one person. So first of all, we shortcut these speeches to 2 seconds because it was very big data, and also we wanted to see that if we can have shorter ultrasound frames or features or X vectors, and with these shorters we can still have good distinguishable features. So we did first of all we cut speeches or utterances to 2 seconds, and each second for ultrasound frame per second is 82, so we have 164 frames per second for each utterances. Then we divided data set to two data sets. One data set is for training and another for generalization, which is 50 of speakers are for training and the rest of it for generalization. And after that, we did SPK recognition. And for SPK recognition, we used the like a convolutional neural network, but we have X vector implementation like the previous context work. But the context they used for acoustic data, but we use it on articulatory data. So for SPK recognition, so we have 50 speakers, and each speaker have different session utterances recording. We cut it to 2 seconds, and then we have 50 speakers and 34 later for a generalization. We wanted to check it. We did, implemented SPK recognition, and we consider different segment length to see if each utterances can still if we consider different segment length, for example, 21 to 164, which is the whole utterance segment length, then we saw that for each utterance we can have less error rate for SPK recognition. And then we extracted X vector features from 2 fully connected layers after a statistical pooling layer, which our statistical pooling layer here was global average pooling. And then we analyzed that if our X vector extracted is good enough or not. So we trained for 50 speakers, and then we generalized it over 31 speakers. Then we did 2 computations to see if our X vector features are good enough. First one was cosine similarity distance. In cosine similarity, we did it for the same speakers versus different speakers. So for the same speakers, our cosine distance was close to the 0 according to the randomly selected X vector features. And another computation metric which we used was a simple 1NN classification according to the leave one out experiments. And it was correct if for each X vector features, the closest X vector feature was the same SPK's ID. And we saw that for first fully connected layer, it was less than the second one, which was 500 neuron. After that, okay, we wanted to generalize for speech synthesizing. Then after that, we have to concatenate the X vector features, which is speaker characteristics to independent speech synthesizing. But for concatenating together, because our input features are ultrasound frame, then these are images, but X vector are not image. So we feed it to different two different layer. One layer for X vector, which went to the dense layer, and another one went to the convolutional neural network, which was convolution 3D neural network. And then these two concatenate together, and then some processing, and then this produce multispectrum features. So as I told, we had two data sets. One was TIL1 and another was TIL80. TIL1, as you can see in the first row, we had like 250,000 frames per second. And okay, we have a lot of data. Then we have intelligibility speech, which is the error rate for development is 25%. And for multi-speakers, over 31 speakers. Without X vector, it is 60. And with X vectors, which we integrate and concatenate with our ultrasound frames, it decreased the error rate. But still, we had very less frame in compare of one speaker. Yeah, thank you.
Please. We are now on time, even earlier, so thank you for being quick. Any questions? There are no questions in the audience. I mean online.
So hello? Hello. Looking at your results, the difference with the additional X vector doesn't seem so high, but did you have a statistical analysis? How big the difference is? I guess it's significant, is it?
Which?
If you add the X vector in the multi-speaker setup.
Yeah, it's slightly better, not too much, but it was the first experiment, so we just saw that X vector could improve it. And actually, we tried that X vector, if is it good for speech recognition. Then this X vector features, according to the constant, the similarity and 1N and classification was good enough for speaker recognition, and give us good speaker characteristics. But yeah, it was in our plan to do some other statistical pooling, like STD or matching networks. Yeah.
And did you consider working on the mismatch between the alignment also with image registration methods or like image processing based approaches?
No, it wasn't in this.
Thank you very much.
You're welcome.
No, go ahead.
It's quite an interesting work. Thanks for that. And I was wondering, like, given the kind of data you have, did you think of mapping it to the articulatory space? Like, because you have